Okay, so we've got a pendulum stationary at t equals 0. And at position y equals -1. Okay, so we can set up the equation. Again, if the pendulum is undamped, now if it's damped you'd have a y prime term in here too. You can think about how that might complicate things. Might not be too bad. Okay. The only force that's going to be exerted on this thing is this. Now there is a restoring force. Okay, this is only external force. Your restoring force comes out as, the force is proportional to y, and y double prime is your acceleration and all that stuff. So y equals 1 at t equals 0, that's y of 0 equals 1, -1. And y prime of 0 equals 0. So we do our Laplace transform. So I'm just going to say, okay, we Laplace transform this, we Laplace transform this, and we get s squared L of y double prime, L of y, and then it's minus s y prime of 0, but y prime of 0 is 0, we don't need that. But we do have the s times y of 0 now, and this is where this model is going to differ from the one we did earlier. So that's s, well, it's s y prime of 0. It's sy of 0. And y of 0, of course, is -1, so that's going to make this negative s. Then the Laplace transform of the delta function is just e to the -2 pi s. This gives us s squared plus 1 times I won't even say what I was thinking. Got to have this too. We do have s squared plus 1. And I'm back to what I was originally thinking. Okay, s squared plus 1 L of y is obvious, equals, okay, we're going to get a negative s here. Add that to both sides. We're going to end up with e to the -2 pi s plus s. So we got something new here. So that L of y can be written as e to the -2 pi s over s squared plus 1, which is just going to give us a shifted sine function. Then plus s over s squared plus 1. So that y equals the inverse transform of e to the -2 pi s over s squared plus 1 plus the inverse transform of s over s squared plus 1 okay. This is just a sine of t, but shifted 2 pi units. Okay, so it's a sine of t shifted 2 pi units. Well, that would be written as Started to write a plus there. Sine of t minus 2 pi. That's the sine shifted 2 units to the right times u of t minus 2 pi plus the cosine of t. That's should be a familiar transform by now. Okay? So there's our solution. What does the solution look like? I'm trying to make sense of it. If I got all my signs right. You're going to be out of phase. Sine's going to stay in phase. Cosine is going to do what it does. So you're going to have the cosine function imposed on the sine function. And I don't know that that matches intuition, because the solution really ought to match the phases. Maybe I'm thinking too hard. Okay, let's just write it out. Okay, so what's this look like? Well, without doing too much with the translation, but let's color code things a little bit. Okay, the sine of t minus 2 pi, u of t minus 2 pi. Going to come out here. T equals 2 pi. Excuse me. I'm glad when allergy season goes away. Okay. That function is going to just be like so. Okay, so you can go 2 pi units of time before this function kicks in, because this function kicks in due to the impulse. It's due to the impulse, and that's exactly the way it comes out of the equation. This term here comes out of the impulse. Becomes this and becomes this. So the inverse transform of what you get from the impulse is this. So there it is. And that's going to be superposed on your other function, which is cosine of t. And I'm still looking for what I have right here. Okay, cosine of t starts here. It's going to have a minimum here. And it's going to be back up here. So it's going to come down like so. Oh, got a little carried away there. And then it's going to do the same thing. It's going to have a minimum here, and it's going to be back up here. So I didn't do a real good job of that. The amplitude of this thing should be the same as the amplitude of this thing. So I've got this a little bit too low. Both of these should be at the same height, but we still see what can happen. If we superpose these, we get our final function. Okay, tracing the purple graph from here to here, going to look like this, because we're adding the green graph, which is this, which is 0. And then we add these two graphs, which means that, remember, the amplitude of this graph should be as great as the amplitude of this graph, so this should really be up higher. This function is not going to reach 0 until the purple graph is much lower than the axis, as the green graph is higher. So it's probably not going to reach 0 till you get here. Then it's going to be 0 again where these two match, it's going to be 0 like here. Going to be kind of monstrous. It's going to reach a higher peak than the cosine function itself would. So we're going to have kind of discontinuity in the derivative. The thing is going to start going up. Cosine isn't changing much here. The sine is changing rapidly. So this thing is going to kind of go up and peak maybe like here before it starts coming back down. Then it's going to come back down lower than either of the two functions, and it's going to do this. So we're going to suddenly change from a cosine with an amplitude of 1 to a cosine with an amplitude of, I believe, square root of 2. You know, being in brain fog, I can't work that out quickly in my head, but I believe that might be it. In any case, it's going to have a bigger amplitude. What's not clear is that the amplitude of this green function should be equal to the amplitude of the purple function. So if you draw it correctly, it's going to look like that. Now your book is going to say, okay, now you go to software and graph the thing. Well, you don't need software to graph that. You just use your you know, sum of two angles formulas and stuff like that. Stuff you can easily derive from Euler's identity and work it out. Gives you better intuition. Of course, my intuition led me to amplitude of square root of 2, and you can check out and see just how good my intuition was on that. All right, well, that's a little different behavior, and it's a little different than the behavior I think you see in the example in the text, and actually I probably have that close by here. See what the graph looks like. Yeah, in the text it's struck at a different position. And you know, I might have done something wrong there. Okay, we have that. Let me look at what I did here. Can't look, it's not there. Oh, never mind. Thought I'd done something wrong, but I didn't. Okay, there's an example. Now let's go ahead and get brave and see what we can do if we apply the impulse while the thing is still in motion, because at this point when we applied the impulse, the purple curve, the cosine function that this thing follows up until the impulse, is just leveled off so that there's no velocity. What if there's a velocity? How does that work in? So let's see how that plays out.